Hello everybody. In today's video we are going to learn something known as unmodulated CW radar. Okay. So in the very first video or in this series I had explained about primary radars and the principle of operation of primary radar. And in the second video I had explained about CW radar, and we learnt how a modulated CW radar works like, right? So in the pulsed radar as well as in the modulated CW radar, what we saw is how these two radars can compute the range of the target. Okay, but both these radars, they cannot compute what is the velocity of the target. Okay, so that can be the velocity of the target, the velocity at which the target is moving towards the radar or moving away from the radar. Okay, so that can be found out using something known as unmodulated CW radar, which operates in the principle of a Doppler shift. Okay, so we'll talk about that. So this was like a primary radar where we saw the max range equation which we derived. So we sent a pulse and then we computed the total time taken by the pulse to go to the target and come back, and with that the range of the target was computed, right? And then we talked about modulated CW radar in the second video, in which the transmitted signal was continuously being modulated, so it was changed, and now once you receive the signal, so you will find there is a difference in the signal that is being transmitted and that is being received, and that difference is proportional to the distance between the target and the radar. So again we derived that equation for that. Okay, and both here and here the drawback was the velocity, and you cannot find out the velocity of the target, only the range can be found, right? So there is something known as unmodulated CW radar, which operates which uses the principle of Doppler shift. So let's first try and understand what is Doppler effect is. Suppose I have an antenna and an aircraft, right? So if I'm say transmitting some signal pulses at a periodic interval to the some packets of RF energy I am sending towards the aircraft, it's going and getting reflected, and initially let's assume the aircraft is stationary, it's not moving, right? So if I am transmitting say at 0 nanosecond, 0, 1, 2, 3, every 1 nanosecond I am sending a pulse, and if the travel time is 1000 nanoseconds for this packet of energy to go hit the aircraft and come back is 1000 nanoseconds. So I would be receiving at 1000, 1001, 1002, 1002 nanoseconds, right? So if I see the transmitting frequency is 1 gigahertz, right? So at every 1 nanosecond I am transmitting one particular pulse, and I am receiving it at every 1 nanosecond. Okay. So as long as it's stationary, so the transmitting and the receiving pulse frequencies will be the same. Now let's take a second case where the aircraft is approaching the radar, right? So I transmit the first pulse, okay, and I receive that, and the total distance traveled will be right proportional to the 1000 nanoseconds. So I'll receive it at 1000. Okay. But the second pulse, that doesn't have to travel that much because the aircraft has now moved forward, right? So it has to travel lesser distance. So instead of receiving at 1001, I could receive the second pulse at a time slightly early than 1001. Say just I am giving an example of 1000.5, right? And again the third pulse, again that need not take again 1000 right nanoseconds for travel because the aircraft has further moved ahead. So if you see the receiving frequency, right, it will be more than 1 nanosecond, less than 1 nanosecond. You will keep receiving it because the consecutive pulses will have to travel lesser. So this frequency at the received frequency will be higher than the transmitting frequency, right? And that is known as the Doppler shift. Now if I have to find out what would be the Doppler shift, okay, so that is nothing because this pulse is going and coming. So the total shift in frequency will be what? It is distance divided by lambda, right? So 2 dr by dt. Okay, that is the total change, the frequency drift which would happen. Okay, or the Doppler shift which would happen. Okay, will be 2 into dr by dt, right? And dr by dt is nothing but the velocity. So you find that the Doppler shift okay, which is happening, which you will observe. Doppler shift is nothing but the shift from the mean frequency which you are transmitting, right? So the change in frequency will be proportional to the velocity with which the aircraft is approaching the target or leaving the target. Okay, so this is the formula. So this principle is made use of to compute the velocity of the. Now this is the block diagram, right? So you have an radar transmitter. It's transmitting certain frequency with the help of an antenna. Okay, although in this block diagram the transmitting and the receiving antenna is shown the same, but that's not generally the case. You will have one transmitting antenna and a different receiving antenna. So what is being transmitted is F0, and what is being received is F0 plus minus Ft. So why is it plus and minus? Because it would be plus if the target is approaching the target, and the Doppler shift will be negative in case the target is moving away from the radar. Okay, so that's why you can have either a plus or minus. Okay, so now a portion of the transmit, a small amount of transmitting frequency is also being routed towards the mixer. Now the mixer gets these two signals, the received signals and a portion of the transmitting frequency, right? So when you mix these two, so I get a beat frequency. Now I can amplify the beat frequency. Now we already saw that the beat frequency is proportional to the velocity, so you can accordingly do a calibration and show on an indicator what is the speed. Obviously here, if you see here, the sign of the FD is lost. Okay, so this only gives the velocity and not the whether it won't indicate in this particular block diagram, it won't indicate whether the target is approaching or it is leaving the target. Right, so it is so whether the radar is approaching whether the aircraft is approaching the radar or leaving the radar. Okay, so you can't only the velocity component can be detected here. Okay, now see, this is the frequency response, a desirable frequency response of the beat amplifier. Okay, so it should not amplify the DC signals. Okay, what the DC signals, what is the signals which are close to DC, that will be the reflections from the stationary objects, right? So because we are interested only on the velocity, so here close to DC signal. So if there is a stationary object, then the received signal will be close to, right, F0 itself, right? So and hence so all those we don't want. So whereas the moving objects, the Doppler, there will be a significant Doppler shift. So close to DC we don't want that, and then this at higher frequencies, okay, we don't want these also, because this is the expected range of a Doppler shift. Okay, so that is how this is the desired frequency response of this amplifier, right? Okay, so here, like I said, this is a more realistic antenna diagram, where you have this is the transmitting antenna, they are the receiving antenna. They have to be different, right? Because you are continuously transmitting and you are continuously receiving. So this is now a portion of the transmitting signal is being given to the mixer, and this is the received signal. So obviously the received signal, you have a low noise amplifier, and then you beat these two, you get the Doppler frequency, and the Doppler frequency is, you are amplifying it and calibrating it, so that finally the Doppler frequency in terms of velocity is being available as an display here. Now if you see here, if you have a system like this where you just have a single RF amplifier, right, which selects low noise amplifier, which selects only the desired signal, that imposes serious constraints on the design of this low pass amplifier. Okay, so it has to so there will be selectivity issues, right? So what we can have is, instead of having, you can have a super heterodyne. So there is a video of mine on super heterodyne receivers, where I have discussed the advantages of using a super heterodyne receiver. So those who are interested can have a look at that video also. Okay, and now what is being done in super heterodyne CW Doppler radar is, you have an additional oscillator which is oscillating at an IF frequency. Okay, IF. So you have an IF amplifier in between inserted. Okay, say it could be 500 kilohertz. So here also, so this is going to generate 500 kilohertz. Now this transmitting a portion of the transmitting frequency is coming to the mixer. It is beating with the local oscillator frequency here, and generating. Okay, and then you select one of the side bands. So so the transmitting frequency plus the IF. Okay, that is what you get here. When you mix these two signals, you get the sum and the differences of both these signals, right? So and you get F0 also. So F0 plus IF and F0 minus IF. So that will be available here. From that, I am just taking, I am using only one of the side bands, which is F0 plus IF here. And this is the received signal, F0 plus minus FD. So when I beat these two, obviously F0 goes, and instead of getting an FD, now since I have an IF also, so I have IF plus minus FD. So I can use the IF amplifier. Now if you see here in the previous, this is the amplifier which was used, okay, to select the desired frequency, because in the atmosphere you will have all kinds of RF signals, right? But this cannot, no, since it is an RF amplifier, the selectivity will be poor. So I will not be able to select the exact desired frequency, right? So by using a super heterodyne reserve radar, I can have an IF amplifier, right? So if I have an IF amplifier, so that helps me in selecting the correct desired frequency. So the selectivity is improved. Okay, but if I so the lower the IF frequency, my selectivity improves, and if I have but then the image frequency also gets into the receiver, and if I have a large IF frequency, I can remove the image frequency, but then the selectivity goes bad. Okay, so to understand about super heterodyne receiver and the design aspects of IF amplifier, please refer to my lecture on super heterodyne receivers. Okay, so coming back to the radar, so what I have an IF frequency here, so F0 plus FD is available, F0 plus IF is amplifier here. So now I have on top of the IF frequency, this FD is, I have this FD coming here, right? And then I do the amplification and then remove the IF in the detector here. Now I have an FD which can be routed towards an indicator. Okay, so this is the more realistic block diagram of an CW radar. Okay, now there's another issue, and now this is ideally this is the spectrum of the received signal. This is how it should be, right? But then suppose but the cross section being offered by the target will not be constant, because it is moving, right? So you will find that subsequent so there would be a change in the frequency also, in the spectrum also, because of the change in the target aspect ratio. Also, you are not going to continuously keep watching the radar is not going to continuously keep tracking the target, right? So that is another issue, right? So and also echoes from the propeller driven aircraft and all, they also spread the spectrum. Okay, so this is the kind of received spectrum practically which we see. Okay, so if the target is exactly moving, if the aircraft is exactly moving towards the radar and there is no change in aspect ratio, right? In that case, right, and in that case you might get this kind of response spectrum, right? But that doesn't practically happen. So you will find that this is the kind of response which you can frequency. So it is spread over, right? So you can say you have a kind of in the time domain a small window is there, right? So so if you in the time domain, if the RF signal is being captured in a small window in the frequency domain, that will result in spreading of the frequency components. Okay, so this is what happens. Now if that happens, then what we can do is, right, we can have an IF Doppler filter bank. Okay, so each of them can be tuned like this. These are all representing each of these filter, the response of this filter. So an appropriate filter can be decided. Okay, so that to eliminate the noise coming from right, and just to select the only the desired Doppler frequency. So you could deploy a Doppler bank within the CW radar receiver. Okay, so that is how this works, right? And now the problem with here and here and here is that the direction of the target is not known, only the velocity is known, right? So now if I am also wanting to know whether the aircraft is approaching the radar or the aircraft is moving away from the radar, then I need to sense the direction or the sign component of FD also. So how it can be done? So this is the transmitted frequency. Initially we said a portion of that is coming to a mixer, and I get an FD out here. Okay, now I can insert one more block here, which is going to shift this transmitted frequency by 90-degree phase shift, and now the received signal is given to this mixer as well as this mixer. So this is the transmitted signal, right? And this is the received signal, right? This is the Doppler shift, and this phi is because there is a time taken for the wave to travel and come back, right? That also is going to introduce an phase shift. Okay, so this phi represents that. Okay, so now I have two mixers here. In these two mixers, you will find in one mixer we are already inserting a 90-degree phase shift. So if you compare the signals, EA, which is being given to this, which is coming out of these two, is there will be there will be a 90-degree phase shift. Now depending on whether omega d is positive or negative, that you are giving to a synchronous motor detector. So depending on whether the Doppler shift is positive or negative, this indicator would this motor, okay, would either move in the clockwise direction or in the anti-clockwise direction. So you can see if it is a plus or minus, it will be lagging or leading. Okay, so that would get interchanged out here. So this can, although in the previous way back in the 90s, 1950s or 60s, we used to have this synchronous motor indicators and all. Now through a simple DSP processors, we can compute the velocity as well as the magnitude, the sign of the WD, okay, which would indicate whether the aircraft is approaching or it is moving away from the target. That can be computed. Okay, so these are some of the applications of CW radar. We have something known as Doppler navigation system, okay, in the aircrafts, right? So you will have three different Doppler antennas, okay, three sets of, right, transmitting in three different axes, X, Y, and Z axis, right? And you will all of them you will have three sets of received signals, and through those three sets of received signals you can compute the velocities, okay, velocity of the on these three different axes, okay, and they can be resolved, right? Because the aircraft axis is also known, right? The aircraft axis also should be known, because the aircraft can be slightly pitching down or pitching up, okay, or it could be rolling towards the left, or so that information also is given to the a processor. Okay, the velocity information in the three axes is given, the aircraft forward velocity, right, the aircraft pitch and the aircraft roll information is also given to the computer, through which the actual aircraft velocity in the X, Y, and Z components, okay, can be found, okay, and then it would give the actual ground speed of the of the aircraft. Okay, ground speed means the speed of the aircraft with respect to the horizon, right, with respect to the ground. Okay, that can be computed. Okay, because if you have a single antenna, it will just give velocity with respect to the and vertical velocity only you would be able to get. But if you have three set of antennas in three different directions, okay, then that you can use that information to resolve the velocity to find the velocity component of the aircraft in all the three axes. Okay, a longitudinal, and a lateral, and the vertical axis. Okay, and so that's what the Doppler navigation system does. Right, there are other applications also, CW radars, like speed guns. Right, these days you have the traffic cops standing in places and are trying to find out if chaps are over speeding. Right, so that also there also we are essentially trying to find out the velocity. Right, and these days most of the autonomous vehicle, they come with a lot of Doppler radars. Okay, which helps us in avoiding collisions. Like there are radars placed not only towards the front side, on the rear side also, which assists in collision avoidance systems. Right, so all these autonomous vehicles, they do come with this. Okay, on the aircrafts, other than for Doppler navigation, we also have radar weather radars which operate on the Doppler frequency. So those radars also, because the Doppler shift induced by the clouds, like, and the storm, they all will be dependent on how thick the cloud is and how much water particles are there. Right, so you get an indication like this, whether this red indicates there it's a bad weather situation there. Okay, green indicates where it's much better, and you can navigate your aircraft through the green patch. Okay, so this is known as a weather radar. So these weather radars also operate on Doppler frequency. So essentially the Doppler shift introduced by a very high dense fog will be different from that of lower dense fogs. Right, so these are some of the applications of the CW radar. So in the next class, now we will try and learn something known about the moving target indicator. So we have already seen modulated radar, unmodulated radar, and we generally spoke about the pulse radar. And now within pulse radar, these are the two categories which we will try and cover in the next class. Okay, thanks a lot.